Okay.
Yes, sir.
So okay. Thank you.
Yes, sir.
Okay. ठीक है, I've heard that. Okay. So last day, the problem that I was discussing. So I did the problem totally myself. Like everything actually, the problem was skipped. Some of the portions were skipped. So the entire thing has many things in it. So that is why I will take more time on this problem. So like the initial things, calculation of the y bar was part of the problem that I had already done, and I hope you have understood how to calculate like y bar for this problem. Okay, sir? So y bar was something which we got the value actually. So y bar was we got it like say suppose uh, so y bar it came out to be something like 22.7. So as we have taken the bottom of the composite shape as our reference, so always 22.7 is being referred from the bottom of the shape that we are considering. So now we are considering the individual sections and trying to find out their moment of inertia. So initially, like the thing that we got confused last day was to hang coach. I don't know why. So the initially the thing that we got confused was, suppose we are having a like semicircle. So if I am having a semicircle, like say suppose this, so we know the moment of inertia that the formulae we wrote, like since it's half of a circle actually, so if I make half of that, for circle it is pi by 4 r to the power 4. So for a semicircle, the I about its base, so if I take the base of the semicircle, so I about the base, the moment of inertia will be equal to, so the moment of inertia will be equal to pi by 8 r to the power 4. So a similar sort of problem has been discussed or is given in the sample problems of the your Merriam and Craig. Just in the chapter. So you go to the chapter of your moment of inertia, you will see the last solved problem that is about this semicircle actually. So for this semicircle, I know about the I base. So initially, I have to find out what is the moment of inertia of the semicircle about its own CG. So let it CG. Let's call it as 1. Since this plane figure we had referred it as to 1. So let's first calculate what will be IG1. So IG1 is the moment of inertia about its own centroidal axis, which I am calling it as x1 and y1. So let's calculate Ix1, or rather we call it as Ig1. So that Ix1 thing that will be equal to Ig1. So the expression will be, so how to calculate that one? So we know that any moment of inertia about any axis. So now we are actually having the moment of inertia about its base. So we have the value for the base. So we have the value for the base actually. So that is why we can write it. So what will be I base? So I base that will be equal to your IG1. So G1 is the centroid. So that is why we cannot write the inverted thing like IG1 is equal to I base and all like this. So we have to write I base that should be equal to IG1 plus A1 D1 square. And now if I intend to find out IG1, so IG1 will be equal to your I base minus A1 into D1 square. So this I base, so what is the value of I base? So it is like pi by 8 into r to the power 4 minus area of the semicircle. So the area of the semicircle will be like pi r square by 2. So that will be pi r square by 2 into the distance between the two axes. So this is the base actually. This is the axis passing through the base, and this is about its CG. So we know that the distance of the centroid of a semicircle from the base is 4r divided by 3 pi. So if I put the value of 4r divided by 3 pi like here, so I can derive the formula for IG1. So from here, if you put all the values, you know the value of R actually. So see in the note actually that I had shared yesterday. So you can do the calculation by yourself, and if you can get the value of IG1. So it's a big value, like something let it when I'm take a short query, I'm just writing it in a short. So it's like, so এটাকে বোধহয় 10 to the power 5 করে দিয়েছিলাম, so it is like 1 2 3 4 5, so 0.43 into 10 to the power 5. So it should be like something 0.43 into 10 to the power 5 millimeter 4. So I hope you are getting this one. So now once you got IG1, now you can calculate what will be the contribution of the element 1, what will be the moment of inertia about the G actually. So now if I draw the figure, so this was the semicircle. Now it is joined. So if I now draw, so this is the centroid of the semicircle, which I am calling it as G1. So I draw an axis passing through G1. So let us call it X1. Let us call it Y, or Y, X1, Y1. And let this be the location of the centroid, which we had already determined from the base actually. So let us consider an axis passing through this one. So this is actually your IG or IX0. Sorry, this is the X0 Y0 axis actually. So let X0 Y0 be the centroidal axis of the entire figure. X1 Y1 be the centroidal axis for the X1 Y1 be the centroidal axis for the semicircle, and X2 Y2 be the centroidal axis for the rectangle, which we will consider later. So since you can understand that X1 Y1 and X0 Y0, so Y is actually coincident. So that is why I have put only Y. The X axis are different for the two figures, but the Y axis is the same. So now if I need to calculate what will be IG, so now if I need to calculate IX0, which I am calling it as like IG for the element 1. So for the element 1, what is the contribution to the moment of inertia resulting from element 1? So IX0, I know IX1. IX1 is IG1 plus your A1 into D1 square. So what is IG1? So IG1 is something like we calculated. So it was like 0.43 into 10 to the power 5, I think. So 0.43 into 10 to the power 5 plus A1. So A1 is again the area of the semicircle, so which is pi r square divided by 2 into D1. So now we need to calculate D1. So how to calculate about D1? So D1 calculate. So if you want to calculate D1, so D1 will be actually the distance between the two axes. So let us call it as D1. So what will be D1? So D1 will be this to this is 4r by 3 pi, and this distance from the bottom, it should be like now if I join, or like let's not join, let's say it's the bottom of the rectangle. So from the bottom of the rectangle, this distance was y bar. So up to this distance was your y bar. So we know this one y bar, and up to this is the side of the rectangle, which is what? Which is your rectangular side ta koto chilo? The side of the rectangle was 25. So the side of the rectangle was 25. So now we need this distance actually. So what will be this distance? So this distance will be এই ডিস্টেন্সটা we need actually. So এই ডিস্টেন্সটা কি করে পাবো? This entire distance is actually your কত আছে? It is 25 actually. So 25 minus y bar. Minus y bar. So আমরা যদি so আমরা যদি d1 টা করি, প্যাডটা অ্যাকচুয়ালি মাঝে মাঝে নিচে চলে যায় লেখাটা খুব, I don't know why, মানে রাইটিং স্পেসটা অনেক হাই, but I cannot get the entire writing space. So like if I want to calculate D1, so D1 will be equal to this 4r by 3 pi part divided by y bar. This is 25 minus y bar, I think, like. Okay, so this will be 25 minus y bar. So am I correct? You're able to get that?
Yes,
sir.
Yes, sir.
Board yotota freedom ache, the freedom that I get on a board here, writing is a bit of challenge to me. Okay, so now you put the value of y bar, you know the value of y bar, you will be getting the value of D1, which is done on the side, I think. You can see in the note, so it will come out to be something like 12.44 millimeter. So you put it here 12.44 mil whole square. So you'll be getting the value of IG1. So this is the moment of inertia about the centroidal axis for the entire centroidal axis of the entire composite shape actually, and the contribution is only from 1. So the contribution for the semicircle is, so it will come out to be something like 2.07 into 10 to the power 5 millimeter 4. Okay, so now we are done with this one. So next is we have to calculate what is the contribution about IG from the rectangle actually. So the rectangle part is easier. I hope you can do that, or rather if you feel like I can do it for you also. So let's draw the rectangle. So just go to the next page. You will see that I have drawn the entire figure. I have tried to draw the figures more than once actually, so that you get the concepts. So this is actually y. So this is the G actually. So this is the rectangle. I have named it like the bottom rectangle. Let it be like A, B, C, and D. So this is the G, centroid of the composite figure. So let an axis pass through this one. Let it be called as x0. And this is the centroid of the rectangle, which should be at D by 2. So if this length is 25, so this length should be 25 by 2. So I hope you can understand that for a rectangle, the centroid always lies at your b by 2 and d by 2. ठीक है sir? So now for the contribution of this rectangle, I have to calculate. So in this case, this should be your d2. So initially, let's calculate what is the moment of inertia of this rectangle. So what is the mi of the rectangle one, rectangle 2 about its own centroidal axis? So its own centroidal axis is x2y. x2 y2. I have put only x2 y because y is same for all the things actually. ठीक है sir? So it should be, so for a rectangle, we know that ix2, or rather if we call it ig2, so that should be equal to, ig2 means an axis passing through g2. So that should be equal to bd cube by 12. So what is the base of the rectangle? So base of the rectangle is like, it's given like, I think it's 50. So 50 into depth cube. So depth of the rectangle given bd cube. So the depth is actually 25 cube. So bd cube divided by 12. So you calculate these values. I'm not writing those. I will be writing the final one. And then same thing you write down mi of the rectangle 2 about, now we are changing the axis, so we need to find out what is the contribution on the centroidal axis for the entire composite, which passes through G actually. So the axis now is x0y. So about x0, what will be the moment of inertia? So let's call it ig. The contribution is coming from 2, the second element, which is the rectangle. So now that should be equal to what? That should be equal to your ig2, the moment of inertia of the rectangle about its own axis, own centroidal axis, plus a2 into d2 square. So this is about how to apply the parallel axis theorem. So this should be ig2, 50 into 25 cube by 12. So 50 into 25 cube divided by 12 plus a2. So what is the area of the rectangle? So the area of the rectangle is like 50 into 25, I suppose. So 50 into 25 into d2. So d2 is this distance. So how to calculate d2? So in order to calculate d2, I hope you can understand that from the base actually, this is y bar. So this distance is y bar. And the centroid of the rectangle actually, it lies at b by 2 d by 2. So this distance will be depth, half of the depth actually. So half of the depth is 25 divided by 2, I hope. Right? It is 25 divided by 2. So what will be d2? So d2 will be equal to y bar minus 25 by 2. So you put the value. So what is the value of the y bar you have got actually? So y bar you have got it to be like 22.7 minus 12.5. So from here you can calculate the value of d2. So d2 will come out to be something like 10.17 millimeter. So you put this value. So you put this value into 10.17 whole square. So you will be getting the value of ig2. So it's something like the value you have got. I'm not writing that one. That's irrelevant because you can do your calculations on your own. Now the mi of the entire figure. So this is, now we have got ig1, ig2. So mi of the entire thing actually. I mean the rect plus rectangle plus semicircle. So I'm writing it SC about the centroidal axis of the composite shape, so which is passing through G. So the axis now is x0, y. So IG, that is having a contribution from 1 and that is having a contribution from 2. So since they're added, you can add them on and you will be getting an answer. The answer to just do it by yourself in your copies and all. So you'll be getting something like, do it because I'm gonna do it at your leisure times because I want to check whether all my answers are correct or not. Okay, sir? Okay, so this is how about calculating the moment of inertia of the entire composite shape that was given to you. Okay, number 1 done. So number 2 is, okay, so now once we are done with this part, next is we have to calculate the moment actually. So how about calculating the moment? So I'm just returning back to the problem. So just there is a good thing to learn about here is we have defined what is pure bending. So what was the definition of the pure bending that I gave you? So the pure bending for the definition of the pure bending was there is no shear forces acting on the element, only bending acts actually, only it is subjected to bending moment actually. ठीक है, there are no shear forces acting on the element and the bending moment is constant. Actually the bending moment doesn't change, it is subjected to a constant bending moment, right? So how to go about that one? So how to calculate, how to see that it is having a constant bending moment? So I was just not introducing that theory of bending moment diagrams and all, because that is all that is in our syllabus and we will be studying later on, but I thought introducing it now itself, because then again I have to come back to this problem. I don't know I will be getting that time or not. So let's calculate, let's do a bit of calculation to show that they have said that,
Sir,
see, like they have,
sir, please
uh,
see if someone is trying to join or not.
acha, acha, acha,
Yes,
okay,
I
look,
am
wait.
getting messages actually.
Sure. স্বর্ণেন্দু, ওকে, একজনকে জয়েন করেছি, স্বর্ণেন্দু। আর কেউ আছে? আর কেউ মেসেজ করছে? এনিওয়ান এলস? একটু ওয়েট
স্যার
করবো
মনে
2
হয় ওই
মিনিট।
ছিল।
আচ্ছা,
স্যার
এক
মনে হয়
সেকেন্ড,
ওই
1
ছিল
মিনিট,
actually।
হ্যাঁ হ্যাঁ ও ছিল, আমি 1 মিনিট ওয়েট করে যাচ্ছি।
আচ্ছা ঠিক আছে স্যার।
জাস্ট 1 মিনিট, আই ক্যান ওয়েট। কারণ if I switch screens I cannot see who is trying to join and who not. So done, I hope আর কেউ নেই, you can see the screens also. Just কেউ যদি মেসেজ করে আমাকে একটু বলো, because when my sharing is on I cannot see the screen.
হ্যাঁ স্যার বলে দেবো।
Okay, so let's get on to the next part that we were discussing, is something why this portion is being called as a pure bending problem. So why I am able to apply the pure bending formula right here. So that's a thing that you should be able to understand, why the pure bending part is applicable on the part BC, not on the part AB. So see, they have asked you to find out what is the maximum tensile and the compressive stresses that are getting developed in the portion BC of the beam. So I am applying the portion I have applied at last in the last solution I gave you there. See, I have applied the pure bending equation there. So you may ask me, sir, why you are applying the pure bending equation here? The forces acting here are actually shear forces. If you, the forces are actually trying to shear. What is the cross section? So if you consider the cross section of the beam and if you consider the forces, actually the forces are shearing the element actually. So the forces are parallel to the cross section. If you see the 4 kilonewton force, that is parallel to the cross section. So there are shearing forces present. Then you may ask, sir, why you are applying the pure bending equation on the portion BC and why not on the portion AB, or why specifically in this problem they have asked you to find out the tensile and the compressive forces in the part BC and not AB. That is something that must come to your mind. So keeping that in mind, so I am just discussing these things, which is also part of our syllabus. Not like it will go on waste. We will start discussing this. Just the next chapter is itself, like the next chapter is torsion, and after that we'll be starting the how to draw shear force and bending moment diagrams, SF and BM diagrams. So in this part itself, I will be able to explain the entire things in entirety to you. So the thing was like we were having a beam like this. So now I am considering the length of the beam, the XY plane of the beam. We are done with the YZ plane. So now I am considering the XY portion of the beam. So I can see that there is a force P acting here and there is a downward force P acting here, and it's fixed like in this end. So these two actually, these are, so they are separated by a distance, say small a, and I hope the other distance is also same actually. So this one was also a, I think. So I'm just taking it as a. It is 300 millimeter, 300 millimeter. Both are same actually. So I have taken like this part as a. So now how to draw a shear force BM diagram? So in order to draw a shear force BM diagram, so I hope you can understand that the loading pattern is constant up from A to B and the loading pattern is constant from B to C. So for the part AB, I can draw a bending SFBM diagram, and for the part BC, I have to draw a SFBM diagram. Because you see from A to B, there is no variation of the shear forces actually, right? So first thing is you have to understand that this plus P minus P, they are actually shear forces. Why they are shear forces? Because you consider the area. So they are acting, the forces are acting on the YZ plane. So what is the YZ plane? The cross-sectional plane. So P is actually parallel to the cross-section actually. So since the force is parallel to the cross-section, what is the effect? We get a shearing effect, that is a shear force. So here in this case, capital P and plus P, they are not tensile forces, they are shear forces. So that is why in beams actually we draw shear force diagram. Are you able to understand? Hello? Yes, no, bolo do. That's enough.
Yes sir.
Okay, very good. So the thing is like, so Amitav bole diche still I am explaining. So if I see like baki kore bolbo I don't know actually. So suppose this is the cross. Suppose this is the beam actually. Any beam, any cross section. Suppose a beam is having a cross section something like this, and I am applying a force somewhere around here. So how the force is acting? So if I take the cross section of the beam, so what is the cross section? You pass a cutting plane or a sectional plane. So this is the cross section. So you see this load capital P. This is parallel to the cross section of the element. So that is why you can tell that. So that is why you can tell that the forces plus P and minus P in this case are actually shearing forces. That is why we have to always draw your shear force and bending moment diagrams. Okay. So Ami Jayata, I have to free this space because I have to draw the. I am not drawing the SF diagram as of now. I am just drawing the BM diagram. Later on, we will be learning how to draw the SF diagram, which is also very easy. So coming back to this one, so how to draw? So we are having 3 points like A, B, and C. So we are considering the portion AB of the beam. So you can understand that actually there are two portions in this beam that are subjected to loading. So the portion AB, from the portion A to B. So if I move from the portion A to B, I can see that there is no change in the loading pattern on the element. Again, if I move from B to C, I can see that there is no change in the loading pattern from B to C. Only from B, if I move from left to right, there is a change in the loading pattern. So I am dividing into two parts. One is the part AB and another one is the part BC. So I am doing my analysis for the part ABC actually. So what I am doing is I am passing a cutting plane or a section XX. So you can just write down. Okay, it's written in the note. You can write down by yourself whatever you feel like. So we are considering a section XX at a distance small x. So we are considering a section at XX at a distance small x from the end A of the beam AB. So I am considering the portion AB. So that is why I have taken a cross section lying anywhere. So the x is actually changes. X changes from 0 to small a. So this is the load P. So this is the load P and this is the location of the cross section of the beam. So let the moment acting on any at a distance x be given by mx, right? So anti-clockwise I am taking it to be positive. We will be defining sign conventions more when we go to those chapters and all. So now you can understand that anti-clockwise moment I am taking it as positive. So that is why I have put mx. So mx is the moment acting at a distance small x from the end A of the element. So this is the end A. ठीक है? So now if I write a moment balance equation, so if I write a moment balance equation taking counterclockwise moment is equal to 0. So what I will be left with? So I will be left with something like, so mx is positive, and what is the moment of this force P? So this distance, I have taken the moment at a distance x. So mx, so P, the moment is actually at the point xx, the moment due to P is clockwise. So I can write it like mx minus px is equal to 0. So what I should be having? So I am getting mx is equal to px. So you can see that this is y is equal to mx equation. So you can see that the moment actually varies with the distance x. It is not constant from a to b. It actually varies from the distance a to x. So if I write that down, so let x is equal to, so at x is equal to your 0. So at x is equal to 0 means which point? I am at the point A. So ma is equal to 0. So at the point A, the moment is always 0, is 0. At x is equal to small a, what I should be having? So at x is equal to small a means mb. So that should be equal to p into small a. So what is this variation? This is a straight line. So now let me draw the bending moment diagram. So I'm just drawing the bending moment diagram. I am marking off 3 points corresponding to this. This is the point corresponding to B, and this is the point corresponding to A. So from the point A to B, I can see that there is a linear variation of the bending moment. So this is the bending moment variation from the point A to B. So for the part AB actually, so for the part AB, the bending moment varies linearly and it increases from 0 at A to PA up to the point B. So this length is actually PA. I'm not writing that. I will writing that later. So this is y is equal to mx. So this is varies. So m varies. So on this portion, m varies with respect to x. It's not constant. So that is why the portion AB is not under pure bending, because we have defined in pure bending that in the pure bending part actually the bending moment remains constant actually. But you can see that for the part AB, the bending moment is not constant. The expression is mx is equal to px. So bending moment is 0 at the point A and the bending moment becomes maximum at the point B, being equal to PA. So the crux of the thing is like the bending moment is not constant in the part AB, or the part AB is not under pure bending. So that is why they have asked you not to apply the pure bending equation on the part AB, but for the part BC. They have specifically written in the problem that just you find out the stresses using the pure bending equation on the part BC. Why not AB? Because AB is not at all in pure bending. Then let's do the same thing for the part BC. So portion AB is done. My space is very short, so I have to just skip to the other page. We will be returning to that page once we get the values of the bending moments and all. So again, let me draw the figure. So this was the force plus P. This is a force of minus P, and they are separated by a distance of small a. So now I am considering the bending. What is the bending moment which occurs in the portion BC of the beam? So for the portion BC, so let this be A, B, and C. So what I have to do is I have to take a cross section in the part BC, and now I have to draw the the equilibrium diagram, or the free body diagram for the part AX. So this is the AX part. You can do it from the right side also. Just to remind you, this can be done from the right side, taking right side balance also. You have to find out the reactions and all, which will be done in the next problem I have shared yesterday also. So let's do it from the left side. We'll be getting the same answer since the beam is continuous. Okay, so এইটা হচ্ছে দেখো এখানে there is a force of capital P, আর কি আছে beta, we have crossed B, so the force at B will be there, and here is the x time into dure ekage, it's exaggerated, so don't get confused, huh? So now, so this distance is, so from the point A, this x is at a distance of small x, and what, so, and this distance is small a. So this is A point, this is B point, this is xx point. C is A dike ache, C is to the right of this point. Don't get confused, don't draw parallel lines and all. So now let's calculate what is the moment at the section XX. So XX lies between B and C. So for this portion, so let us write a moment balance equation. So now if I write a moment balance equation taking counterclockwise moments as equal to positive, so what I should be having, so Mx is counterclockwise. So Mx is there. So what is the moment for this force capital P? So this should be equal to Px. This force is P and the distance from the point is X. So this should be Px. So P, this is causing your clockwise moment. So minus Px. What is the moment for the other force? So what is the moment for the force at B? So the force at B is actually causing a counterclockwise moment, and its value will be P into x minus a. What is this distance? This distance will be x minus a. So you can write it as plus P into x minus a is equal to 0. So see, this actually gets cancelled, px. So you are left with mx is equal to P into a. So what is this? See, this doesn't depend on x. So mx actually doesn't depend on x. So this is a constant. So this is a constant moment. So the moment from the point B to C is actually constant. So now if I need to complete the bending moment diagram, so the bending moment diagram is this actually. So this is the final bending moment diagram. So this is PA. So this entire thing, so this is the bending moment diagram. So this is ABC. So this is the bending moment diagram. So you can see that the bending moment for the part AB, it actually varies. So this actually varies. So if I need to find out, suppose you are given a point, say x is equal to a by 2. So suppose someone asks you find the moment at the point x is equal to a by 2. You can put the value here. So that should be PA by 2. Or you can do graphically also, just you plot it on a graph and then you can calculate what is the value of the moment there. So for the portion AB, the bending moment is not constant. It varies with x, linearly varies with x. So that is why I have joined it using a straight line. Later cases may come where there can be cubic variations, quadratic variations and all. We have to draw such curves. But for the portion BC, you can see that for the portion BC, the bending moment doesn't vary with x. It is actually constant. So the portion BC is actually under pure bending. So since the portion is under pure bending, that is why in the problem they have asked you to calculate the shear stresses using the pure bending equation in the portion BC, not in the portion AB, because on the portion AB, you cannot apply the pure bending equation because the portion AB is not at all in pure bending. Because for the portion AB, the bending moment changes along x actually. But for the portion BC, the bending moment is constant, PA. So you see that for the bending moment, so bending moment is constant from B to C, but over the beam actually, over constant over BC, over the part BC. So this part portion BC is actually under pure bending. So this actually clarifies the point of pure bending and why in this problem they have asked you. See, now I'm going back to the problem. See, they have categorically stated that for the problems 4.9 to 4.11, you find out the stresses on the portion BC of the beam. I will be doing this one also. I will be doing like this one also. ठीक है? So the portion BC is under pure bending. Why? We have drawn the bending moment diagram and this one is the final bending moment diagram. So if you see in the bending moment diagram for the portion BC, the bending moment is actually constant and always equal to P. It doesn't change with X. It has no variation with X. So you can apply the pure bending equation on the portion BC of the beam. Up to this clear?
Yes, sir.
Okay. So now we
Yes,
are
sir.
done. So now we are done. So the next part. So this is about. So we learned two things. Number one is how to draw bending moment diagram. So BM diagram, that is in our syllabus. We will be learning that one. So this is about how to draw bending moment diagrams. You have to take any cross section. You just divide. So if you are having a beam, you just need to find out what are the sections that are under same loading actually, or there is no loading change actually. So you take one length. So in this case, we have taken AB, BC. Two sections actually, or two portions of the beam, and then we have taken a section on AB. So how I need to find out how if I change X from 0 to A, I need to find out what is the variation of the moment from A to B. So you have to pass some sections from the on the portions, and then on those sections you have to write the moment equation and you have to find out what is the relation of M with X, how M varies with X, or how the moment actually varies with the span length of the beam. So X is actually the span actually, or the length of the beam. So how the moment actually varies along the length direction of the beam. So that is we had found out till now. So that is one learning, bending moment. Number two is again we revisited the definition of pure bending. So the portion BC is in pure bending, not the portion AB, because as per pure bending, the portion must be subjected to a constant bending moment and there should not be any shear forces and all. I haven't drawn the shear force diagram here. But if I had drawn that, aro confusing hoye jabe. I don't want to go in details actually. When I draw the shear, just remind me. When we enter the shear force BM part, a problem I will just do it. It's just one second job. So you can see that the shear force will be 0 on that portion and it's only having a constant BM. So the portion BC is actually under pure bending, not the portion AB. So now calculating the bending stresses. So in order to calculate the bending stresses, so the beam was something like this. I am repeating. So we got the neutral axis of the beam. Now forget everything. You just draw the neutral axis NA. And this one is Y bar. So this is on the downside Y bar, and on the top side the total length. Whatever is the total length or the height of the structure minus Y bar you do, you will be getting the distance of the top fiber. So this is the topmost fiber. So this is the topmost fiber. I am writing in as TF, and this is the bottommost fiber. So just you have to find out the distance of the topmost fibers and the bottommost fibers. So what will be Y top, Y bottom? So I have written the expressions for expressions you can see, and then to find out the stress on the top part or the top fibers. So let's do the thing for the top fibers. So for the top fibers, what is the thing that I will be having is, so M by I, that is equal to your minus sigma by Y, that is equal to minus sigma top divided by Y top. So you calculate what is sigma top. So sigma top will be equal to what? Sigma top will be equal to your কত হচ্ছে দেখো, minus M into Y top divided by I. So you put all the values. So what will be the value of sigma top? So sigma top will be equal to minus. So what will be M? So M is we got to be PA. M in the portion BC. So that is equal to PA. So PA was something like 4 kilonewton. So 4 into 10 cube into A was C, 300 millimeters. So that is 0.3. So this should be 1200 Newton meter. So minus 1200 Newton meter into Y top is, see I have calculated in the note, so it is 0.027 divided by your 4 point whatever is the value of the I, actually final I you got. So you put the value there. So you'll be getting sigma top is equal to minus your 81.8 MPa. So why minus? Because see, the top portion will be actually in tension. So see, from seeing from the figure, it's actually difficult to understand since you are having two forces, one upward, one bottom. So you have to go by the formulae. So that is why I told you to rely on the formulae also. So from the formulae, actually, you can understand that the top portion will be in compression. So the top fibers I have written in the note. So the top fibers, since the value of sigma top actually came out to be something like negative. So the top fibers are in. So these top fibers are in compression. Similarly, you do the same things for the bottom fibers. So for the bottom fibers, you have to calculate the value of y bottom. So y bottom was y minus y bar, since y bottom is actually below the neutral axis, and neutral axis is our axis system actually. So that is minus y bar. So that is minus কত ছিল? It was like 0.22, I think 0.022 millimeter, তাই তো? So you do the things like m by I is equal to minus sigma by y. This is the basic equation we got. So that is equal to minus sigma bottom divided by y is our y bottom. So you calculate the value of sigma bottom. So sigma bottom is equal to m into y bottom divided by I. So what is m? M is 1200 into y bottom. So this is negative, sorry, this is negative. And y bottom is your also negative. So minus 0.022 divided by your y bottom. So what is y bottom? It is 4.01 into 10 to the power 5. So you put all the values, this will be actually getting to be positive. So sigma bottom, it will come out to be plus 67.8 megapascal. So this is the thing that you will be getting. So since it's for positive sign, so the top fibers are under tension. So the top fibers are in tension. So this is about discussing the whole problem. So just see whether you are able to understand this problem, or else I will be starting the next problem shortly. কোনো confusion থাকলে জিজ্ঞেস করো. So this is a huge problem. I have taken every bit to make you understand this one. Just let me know whether you can get the concepts. Just let me know whether you can get the concepts of this one. Yes, we will be starting the next one.
Yes, sir.
Anything you want to ask me related to this problem? So big a problem, you don't have any doubts? Huh? কি হলো অরণ্য?
Yes, sir.
কোনো ডাউট নেই?
না স্যার অ্যাজ সাচ কিছু নেই আজকে।
মানে পড়াশোনা হয়নি, এটা পড়া হয়নি এখনো, তাই তো?
না না মানে এই প্রবলেমটা রিলেটেড কোনো ডাউট নেই।
আচ্ছা ঠিক আছে, ওকে।
স্যার
সো
এটা যদি
আমরা তাহলে
আমাদেরকে
নেক্সট
এসপি সেকশনের জন্য বলতো তাহলে আমরা কি করতাম?
এবি সেকশনের জন্য তাহলে আমি ওগুলো আবার পরে ডিসকাস করব। আমরা যখন আমরা মানে আমরা উইল বি টেকিং শিয়ার ফোর্স বিএম দুটো নিয়ে আমরা কাজ করব, কম্বিনেশন অফ বেন্ডিং এন্ড শিয়ার ফোর্সেস, সেগুলো আমরা আসবো পরে আমরা আবার ডিসকাস করব। ইটস এ গুড কোয়েশ্চেন যে আমরা এটা যদি এবি পোর্শনের জন্য বলতাম কি করতাম, what we could have done when if it was asked for the portion AB actually. So we will be discussing those problems because for the portion AB you have to consider both shear force and bending moments actually. ঠিক আছে? So that is also in our syllabus, combination of shear force and bending moment. I don't know how much I can cover. Looking at all the things like এই তো অবস্থা, I have to মানে writing one thing is very difficult for me. So that is why I always preferred board, because writing on a board is easier for me than this. ঠিক আছে? So let us see how much we can cover. So let's move to the next problem, 4.15. So this is problem number 4.5, 4.15 that we will be discussing now. So in the problem 4.15, So this one is the problem 4.15. So this is just the reverse problem. So here you have to find out the largest couple that can be applied to the beam based on the stresses actually. So the allowable stresses in tension and the allowable stresses in compression are given to you. So you have to just determine what will be the value of the minimum moment, what will be the value of the permissible moment that the beam can bear. So going to this problem actually, so you go to page number 53 of the notes that I have shared. So this is a completely different sort of problems. So let us discuss something about that. So first thing is for any problem in beam actually the basic thing is you have to find out the moment of inertia. So for a T section, I hope in the last class you have done the calculation of the bending moments, calculation of the moment of inertia for a T section. ঠিক আছে? Still I will be repeating that one because it's better that you get in sync with these sort of problems. So this is 40 millimeter. The height is like this one is 30 millimeter. Achha, this one is 80 millimeter. This one is 80 millimeter. This is the T cross section beam, and the height, this vertical height, this total height is given like something to be 60 millimeter. Okay? So initially you have to calculate this for the I. What is the cross section? What is the moment of inertia for the T section? So for the T section, actually, as you can understand that again the T section is symmetric about the Y axis. So let's consider let's consider this is X and this is Y. This is X and this is your Y. Any arbitrary. So the base of the figure actually we are taking it as the reference for calculation of the location of the centroid Y bar, and the Y bar will lie on the Y axis itself. Why? Because it is symmetric about the Y axis. So it should lie about the Y axis. I don't know where. I only don't know that it will be lying somewhere like at a position say G, which is like which I have to, whose location from the bottom actually I am calling it as Y bar. ঠিক আছে? So what we do is we divide it into two rectangles. So this is first rectangle. So this is the top rectangle, and we divide it into a bottom rectangle. So each of the rectangles will be having its own centroids actually. So this is G1 and this is G2. Okay, so let's go about calculating. So for the rectangle 1, so I am writing like rectangle 1. So A1 is equal to what? So A1 will be equal to A length koto ache. So the area is 80 into this one 30. So 80 into 30, so that is 2400 millimeter square. Then is Y1. So what will be the location of the centroid? So Y1 is this one. So this distance is Y1. So this total distance is Y1. So in order to calculate Y1, so that should be, this is 60 minus 30. So up to this is 30. So 30 plus, for a rectangle, the centroid lies at b by 2 d by 2. So since the depth is 30, so that should be 30 plus 30 by 2. So 30 plus 15, which is 45 millimeters. So this is for the rectangle 1. And for the rectangle 2, the bottom rectangle, so what should be A2? So A2 will be equal to your, this is 40, this is 30. So this is 40 cross 30. So that is equal to 1200 millimeter square. And what will be Y2? So Y2 will be equal to koto hobe? So Y2 is this one. So Y2 will be equal to koto hobe? This distance is 30. So Y2 will be equal to 30 by 2. So that is equal to 15 millimeter. Correct? So you put all the values. So since the two figures are actually joined together, so we can find the combined location of the centroid Y bar, which should be equal to A1 Y1 plus A2 Y2 divided by A1 plus A2. So you put all the values and do the calculations. So you are getting the value like 35 millimeter. Okay? Correct? Up to this clear?
Yes, sir.
Okay, so we are done with this part. So now how about calculating the moment of inertia of a T section? So in order to calculate the moment of inertia of a T section, so just draw the rectangles again. So this was the top rectangle. So this is the axis.
Sir,
বলো।
sir, Y bar 35 millimeter কি করে আসে? Total width তো 30 millimeter.
Total width না তো 60 millimeter total. Total
স্যার
depth
আপনি
is
ডবল
60 millimeter.
স্যার আপনি বইয়েরটা থেকে ডাবল নিয়েছেন স্যার
So question এ 30 দেওয়া আছে।
আচ্ছা আচ্ছা, এটা আমি অ্যাকচুয়ালি অন্য বই থেকে নিয়েছি অ্যাকচুয়ালি। ঠিক
আচ্ছা
আছে, এটা আচ্ছা আচ্ছা আচ্ছা, দাঁড়াও আমি তোমাদেরকে আমি আরেকটা বইয়ের কথা বলেছিলাম না, যেটা তোমার ওই একই বই, মানে ইটস জাস্ট বিয়ার এন্ড জনস্টন অলসো, আই উইল বি সেন্ডিং ইউ দ্য প্রবলেম। ঠিক আছে, মানে এটা দিস ওয়ান ওয়াজ দ্য প্রবলেম ফ্রম দ্য ডিফারেন্ট বুক বিয়ার এন্ড জনস্টন, আই উইল বি শোয়িং ইউ দ্যাট ওয়ান। ঠিক আছে, just you refer to the things that I have mentioned, মানে I have taken double of the things, I hope. ঠিক আছে, so just whatever are the dimensions, you make them double. You can do this problem also at your home, just take it as an assignment, nothing else. Just learning the concepts is what you have to learn. I have shared that book, I hope, right? That's Beer and Johnston, which contains both statics and strength. সিআর কে একদিন পাঠিয়ে দিলাম না?
হ্যাঁ স্যার, মনে হয় পাঠিয়েছিলেন, ক্লাসরুমে ছিল ওটা।
ক্লাসরুমে দিইনি, আর কনফিউজ হয়ে যাবে বলে। Not in the classroom. I have. See, there is a Pierre Johnston book where this, it's given more concise actually. So that book contains both statics and mechanics actually. So that when I was in university, that helped me a lot because I can at least refer to statics in the same book. So that helped me a lot. So that is why I used to follow that book. So my notes are actually based on some other problems are from that book. ठीक है? So just the dimensions that I told, just put them. So this is the first figure. So had this rectangle been alone, so let this be the top rectangle. Had this been alone, so since y-axis is same for all the ones, and so I am putting it like x y only. So this is x1 y1 or x1 y. So this is the centroidal axis for the individual top rectangle. So for the individual top rectangle, so what should be IG1 or IX1 if you say? So IG1 is the moment of inertia of the rectangle 1 about an axis passing through its centroid G1, or about its own centroidal axis. If it were a alone rectangle, if it were a free rectangle, what is the moment of inertia about its own centroidal axis passing to the point G1? So the formula is, we know it's BD cube by 12. So B is actually your 80 into D cube. So B into D cube was your 30 cube. B D cube by 12. Okay. So now what we have to do is, we have found out the value of G. So G is somewhere around here. So G is somewhere around here. So let x0 y0 x0 y0 or x0y represent the centroidal axis of the T section. G1 is the centroid of the upper rectangle. Capital G is the centroid of the T section. Okay, the centroid of the two rectangles combined. So now if I need to find out IG1, so what is the IG1 or IX0 if you say? So that will be equal to ki habe? So I have to apply the parallel axis theorem. So that is equal to 80 into 30 cube by 12 plus A1. So A1 into D1 square. A1 into D1 square. So whatever is the first part you calculate plus A1. So what is A1? A1 is 80 into 30. 80 into 30 into D1. So what is D1? So D1 is actually this distance. So how to calculate D1? So from the bottom actually. So let this be the base of the rectangle, base of the other rectangle. So we got this one. So up to this is y bar. So from here to here. So from here to here, this value is y bar. Right? So এটা যদি তোমার y bar হয়, so কি করব? So D1 টা কত হবে? D1 will be equal to
y1 minus y bar.
তোমার তো আবার উপরে ওইটা মাইনাস করতে হবে না? দাঁড়াও, D1টা কি করেছিলাম দেখছি, দাঁড়াও। 45 minus 35
10 হবে স্যার।
হ্যাঁ, আচ্ছা, দাঁড়াও। So what I did was, the entire length is 60 actually. So entire length যদি 60 হয়, আচ্ছা আমাকে শুধু এইটা বের করতে হবে D1. So I have to find out this D1. So this D1 will be, so if this is 35, so y bar হচ্ছে 35, entire length is 60. So this should be কত হবে? 35, 25 হবে, up টপটা হবে 25. So it should be
টপ থেকে কেন নেব?
স্যার আপনি টপ থেকে নেবেন, আপনি
IG1
থেকে নেবেন।
হ্যাঁ, তো G1 টা কত হচ্ছে বলো? G1 টা হচ্ছে, G1 is your
G1
actually
মানে তো
60 minus,
y1 টা হচ্ছে G1 এর ডিসটেন্স,
হ্যাঁ,
আর y বার টা হচ্ছে d ডিসটেন্স। তাহলে এটা d1 টা তাহলে y1 minus y বার হওয়া উচিত না?
y1 টা পাচ্ছি না তো, আমি তো 8 লেন্থে জানি। I know this one is 60 from bottom to this one is 60. I know this distance. I know this distance. This distance
স্যার
I know.
আপনি তো
This
ওয়াই
one is
ওয়ানটা
60.
ক্যালকুলেট করলেন, না না ওয়াই ওয়ানটা তো আপনি ক্যালকুলেট করলেন, ওটা
আচ্ছা
45
y1
বেরোলো
টা
ওয়াই ওয়ান।
করেছিলাম না? কত
হ্যাঁ
বেরিয়েছিল
ওটা তো
y1
দেখবেন
টা? হ্যাঁ হ্যাঁ ঠিকই বলেছো।
45
আচ্ছা আচ্ছা।
স্যার,
কত বেরিয়েছিল ধরো, ওটা আমি লিখিনি।
45।
45 এক্স্যাক্টলি। তাহলে আমি করতে পারি 45 মাইনাস y বার। ঠিক আছে, ওকে ওকে, সেটা করা যেতে পারে। সো d1 will be equal to your y1 minus y বার করে দাও একবারে, এটা বেশি ইজিয়ার হয়ে যাবে। তাহলে 45 minus 35, so it is 10 actually. So here you put the value, so it is 10 square. ঠিক আছে, সো এটা জাস্ট ক্যালকুলেট করো। সো ক্যালকুলেট, এটা ঠিক আছে তো? কে বললে এটা? অরণ্য না?
হ্যাঁ স্যার।
ঠিক আছে, এটাই বেটার হবে। সো অলওয়েজ টেক দি হেল্প অফ y1 অ্যাকচুয়ালি, ঠিক আছে? সো দ্যাট উইল বি হেল্পফুল। So এটা কত আসছে দেখো, so just calculate this one. This is coming to be 420 into 10 cube millimeter 4, I think. So do the things, do the calculations from your end. That's why I don't share notes actually, because since the calculations are done, you don't do it at all. Other times I used to ask the students to do the problem and say, and tell the answer to me. So that's a good thing about sharing notes. So এটা হয়ে গেল. So this is about the first rectangle that I am done. So next part আমি করি. So let's do it for the bottom rectangle. Let's wipe this portion out. So এটা আছে. So now what we have is, so on the bottom I have a rectangle. Now wait. So G tech 2, let me wipe this G also. So now I'm drawing the bottom rectangle. So now let this be the bottom rectangle. So this is G2. So this is G, and so let me pass an axis to this one. So let x2y be the centroidal axis for the element 2. So now let's calculate what is IG2 or IX2 rather. So what will be IG2? So let's do it on the other page and refer to the previous page. So IG2 will be equal to again BD cube by 12. So what is base? So what is the depth? So for this rectangle, B is breadth is this one. So this one is 40 into depth. So depth is 30. So 40 into 30 cube by 12. So this is actually 40 into 30 cube divided by 12. So this one, you can write it down, or you can note that this is the moment of inertia of the bottom rectangle or rectangle 2 about its own centroidal axis x2y passing through its CG G2. Now, so the moment of inertia of the rectangle 2 about an axis passing through the CG of the T section, that is x0y. So let's call it as IG2. So IG2 will be equal to your IG2 plus A2 into D2 square. So what is IG2? This is 40 into 30 cube divided by 12 plus A2 is the area of the second rectangle, which is 40 cross 30 into D2. So now again you have to calculate the value of D2. তাহলে D2 টা কি করে পাবো? So this is the value. So this is the value for D2. So D2 টা কি হবে? So D2 will be y bar minus y2. So this is y2. So this is now helpful. So D2 will be equal to y bar minus y2. Correct? So D2 will be equal to y bar minus y2. So what is y bar you have got? So y bar you have got to be 35 minus y2. So y2 was কত করেছিলাম দেখো 15 বোধহয়। So এটা আসছে 20 millimeter. So 20, so into 20 square. You put the value here, you will be getting the value of IG2. So you got the value. So what is the total moment of inertia for the T section about x0y? So that is IG will be equal to contribution from the first element plus contribution from the second rectangle. So if you calculate, you will be getting the value to be something like this, which I had done like 990 into 10 to the power minus 9 meter 4. Just wait a minute. Calculated the stresses and all. Now you are given the stresses, you have to calculate the moments. So in this case, at least you can understand which one is tension, which one is in tension, which one is in compression. So see, so this one is the figure given. So here you can see that the moment, so the moment is actually acting downwards. Okay, so since the moment is acting downwards, so you will be having top side will be tension, bottom side will be compression. Correct. So this is not
Yes,
the
sir.
case we have derived actually. It's a negative. This is the hogging moment actually, convex upwards. So hogging moments one, not the system we derived. For the system we have derived, what was there? It was your, compression upside and tension bottom side. But this problem, as you can see, that there is compression bottom side, tension upside. Correct. So what are the values given? Like top side. So just they have given top bottom. They have given tension compression. You determine which one is which one. Correct. So for the problem. So now in this problem. So let's for the top one. So from the figure, as we can understand, that since a hogging moment, the top one will be in tension, right? So the top fibers, I have drawn it also. So you see that the top fibers will be in tensile and the bottom fibers will be in compression. So let's divide this and do the calculation. So the top fibers will be in compression and the bottom fibers they will be in, so bottom top will be in tension, will be in compression. Right though? So tensile, the maximum allowable tensile stress sigma t is given to you. So what is sigma t? So sigma theta লিখিনি কত দেওয়া আছে দেখো কত নিয়েছি আমি 24ই দিয়েছে সো সিগমা টি the allowable stress and tension that is given to be 24 megapascal. Forgive me, megapascal. ঠিক আছে? And so now I need to calculate the moment. So I have to calculate y top. So what will be y top? So in order to calculate y top, you forget everything. Acha একটা easy. Let's draw an easy figure. So what will be y top? So these are the top fibers. So up to there, these are the top fibers. All the top fibers will be in tension. So this is the neutral axis. I am calling it as Na. So this is y top and this is y bottom. So here, see, like putting signs and all will be just cumbersome. So better is you put mod of m. ठीक है? So let's calculate mod of m because only we need the magnitude of m, nothing else. So what is y top? So y top will be equal to what? The entire length is 60 minus y bar. So this one only you need y bar, nothing else, and the entire length is 60. So y top will be equal to 60 minus y bar. So that is 60 minus y bar was like 35. So this will be 25 millimeter. ठीक है? And what will be y bottom? So you calculate y bottom. So y bottom, so that should be equal to what is y bottom? So y bottom is y bar itself. So y bar is actually your 35 millimeter itself. So you got the two values. So put the value of y top here. So y top, so y top came out to be 25 millimeter. 25 millimeter. So now you put the expression. So what was our formula? So we are having pure bending expression m by I is equal to sigma by y. So sigma top by y top. So what will be m mod m? So I'm just calculating mod m for the two cases. Okay? So mod m will be equal to sigma t into I divided by y top. ঠিক আছে? y টপটা লেখাই ভালো because you will be confusing it with tension, compression and all those things later on. So m will be equal to m টা কত এসছে? So m was your m is given, I hope. ঠিক আছে? M is the value. Okay, no, m is we have to calculate. Sorry, so calculate করতে হবে. Sorry. So sigma top is tension, which is 10 to the power 6 into I is what you have calculated divided by y top is we got it to be 0.025. So this is one value that you will be getting. So it is coming out to be something like 950 Newton meter, as I have calculated. You can do the calculations at your end, and then sigma on the bottom side is under compression. So what is the compressive allowable stress? So sigma c is actually given to be like I think it's 30 megapascal. So sigma c allowable compressive stress is given, and y bottom. So y bottom is given, so or we have calculated. So y bottom came out to be your 35 millimeter. So again you calculate mod m. So m is equal to sigma bottom into I divided by y bottom. So you put all the values like sigma, you have got like what 30 into 10 to the power 6 into your I value divided by YB was your 0.035. You put all the values, you will be getting a value of 849 Newton meter. So what is your suggestion? Which value we take? So we are getting two answers. One is based on the compression. One is based on tension. So which we should apply?
So
Which
the
one we
lower
should?
value.
Lower one.
Always the lower value. Yeah.
Lower.
Because if you give this, if you calculate this one, so just you choose the lower value. You what you can do is you can say someone can say the safe value I choose is 950. Okay, you choose 950. You do a reverse calculation. Calculate this one. You will see that this that sigma c what you get will exceed 30, or it won't be a good design. So whenever you are going for forces, moments, and all these physical parameters and all, always you calculate the lower value. So whenever you are getting the physical parameters, you take the lower value, and whenever you are considering any dimensions, always take the higher value. Dimension problem I have done, I hope. Determination of a diameter we did like a safe determination of a safe diameter for design. We did a problem, I can remember. Hello?
Yes, sir. In second chapter, we have done some this type of.
Somewhere not. We did in the uniaxial loading. We did. There were two cases. We calculated based on deflection and other things. We calculated, and then there came two values of the of the length or diameter. I hope it was diameter. So whenever there is a dimension, take the higher value. Whenever there is force moments and all, always take the lower value. Because you can understand. Because if I choose 950, it will fail actually. Because 858 up to 849, it can bear. Up to 849, it can bear. If I choose 950, so this will be on the compressive side, it will fail. But if I choose 849, it is the stress will be coming to be sigma c. It will be within the allowable limit, and since this value is lower, this sigma t will always be within the allowable limit. It should be something like 18 and all. So whenever you are going for the some physical quantities like moment, force, and all, you always choose the lower values. So from two cases you are getting two values, always choose the lower value. Force, moment, anything you are getting, always choose the lower value. Thumb rule 1 and thumb rule 2 is whenever you are going for any dimensions like diameter, lengths, and all, from two or three cases you are getting two or three values. So always choose the higher value. So for any dimension, if it's higher, it's safe, and for any moment, force, if it's lower, it's safe. That's a basic thumb rule of design. So there are some problems. So 8 problems I had discussed. So you may ask if you have any problems regarding this one. And one problem I have done like 4.11 I have done. It's just a basic thing like I section. This is the I section that I had done. If you can see. ঠিক আছে?
Sir,
Hello?
y টপের ভ্যালুটা 0.05 হওয়ার কথা।
কোনটা?
y টপের ভ্যালুটা ওটা 0.25 তো পয়েন্ট মানে 50 মিলিমিটার আসার কথা ওইটা y টপটা, কারণ জি থেকে তো একদম আপার ফাইবারটার উপর ডিসটেন্সটা নিচ্ছে।
হ্যাঁ তাই তো নিচ্ছি। So this is G actually. So this is Y bar. So these are the top fibers. So this one is Y top. So this one is your Y top. So Y top টা কি করা হবে? This entire length is 60. So up to this is 60 minus Y bar. এটা হচ্ছে 60. 60 minus Y bar. If we do 60 minus Y bar, we'll be getting Y top. So 60 minus Y bar is your 35. So we should get 25. What is the confusion there? I cannot understand.
Yes sir, yes sir. I have
Y top is the distance of the topmost layer.
I have made a mistake sir.
So you have to measure from the neutral axis. Okay? So this is the topmost fibers. We should be bearing the maximum tensile stresses, and these are the bottommost fibers. So these any point lying here, these are the bottommost fibers. So they should be designed based on compression because they are under compression. They don't have to do anything with tension. So these are the topmost fibers which are in tension. Sorry. Top ta ki chilo tension to. So these are the topmost fibers which are in tension. These are the bottommost fibers based on compression. So these has to be analyzed based on tensile stress, allowable tensile stress. They don't have anything to do with compressive stresses. They don't bear compressive stresses at all. And for the bottom fibers, any analysis has to be done based on compressive stresses. They don't have any link to tensile stresses and all. So this is one thing. So if you go to the note, actually another problem like the I section has been discussed. So this is the T section, and shear force calculations are in this chapter. আমি এখন shear force করাচ্ছি না because shear force থেকে questions আসেও না, basically it's just wastage of time. আমরা পরে we will be studying shear stresses or combination of shear stresses and bending stresses, সেখানে আমরা একটু ওগুলো করব, we will be doing those things. So if you go to problem number 411, so 411 see 8 inches, it's given in the note like page number 51 52 51 52 I have solved actually. I will be showing how the why the portion BC is in pure bending. See, I have done it on the new note. I have also mentioned it in a when I have elaborated rather the thing. So সেটা আমি একটু discuss করবো. I will be discussing that. So problem number 411 is your homework. If you want to do it as a homework, do it. If you want to find it as an assignment, whatever way you like. But I would request you to do it at your home. So 4.9, 4.10, 4.11. So these are three configurations. I will be discussing somewhat now 4.10 because it's a U section. Some things to be discussed. Number one, and no more problems on these. Are 8 actor problem. Therefore, 4.4 is given. So this is a cutout cross section. So if there is a cutout, just you can see that when there is a cutout, it will be A1, A2 minus like those things and all. Okay? So when you are calculating the I for a cutout, actually, so you have to write your A1 Y1 minus A2 Y2 divided by A1 minus A2. The things you have learnt in your engineering mechanics. And this problem number 4.4, I hope this is a very, see, this is done in the note actually. So you go to the note page number 49, so you can see that the thing is done. So you are having actually two circular cutouts, two semicircular cutouts from the ends, and you are having a rectangle. So this entire figure, what you can consider is you are having a rectangle, total rectangle minus two circular cutouts. The good thing is that the centroidal axis of the rectangle and the centroidal axis of the two circles are in alignment. So that is why you can directly subtract one from the other. So if you go to note page number 49, you can see that I is equal to I rect minus I circle. So see, directly I have subtracted the things actually. And then based on the things actually, I have done some of the things and then you can calculate the moment. So this is just a different case where you are having the cross sections that are made as a subtraction from basic figures. So I will be doing one of them. So I will be discussing two things. So this one U section. So yesterday or today morning, I think. I hope you have got it or not. I don't know. So problem number 4.9 and 4.9 and like 4. Which one? Wait a minute. So this is not. This is I have discussed. So problem number 4.11 and problem number 4.19. So problem number 4.11 I will discuss, and 4.99 is I am giving you as a homework because I have already shared it in the note. I don't know whether you will be doing or not, but this is just a problem where there is a cutout actually. So this, oh sorry, I forgot. So this I have solved and sent to you to 4.19, and 4.20 I have actually given you as a homework. So 4.20 is a trapezoid. So just find out how you can do it. You can divide it into three triangles, or rather you can divide it into what, like two triangles and a rectangle, right? Problem number 4.20 I am presenting on the screen if you can like see. So problem number 4.20, what you can do is there is a trapezoid, so you can consider it as a combination of two triangles and a one central rectangle. Achha, problem number 4.19, it's also a thing that I have done actually. You have got this one today morning?
Yes,
Yes,
sir.
sir.
So you can see that in the last page actually 4.19 problem I have solved, and then here also I have to calculate M max actually. So I have done this for a hollow cross section, but the answer I got was something different. In the book it's like 177 kilonewton meter, but what I got was like 180. So if you could solve that one and let me know where I got it wrong. So it's good that I get wrong somewhere so that you can at least correct me. You can spare that time for me. So 4.19 take to try karo, it's given, it's the solution is given to you, but you need to find out where I got it wrong. Okay, number one. Number two is, so it just a small thing was to be discussed by me. So this one, like a problem does. So there is a U section. So you can, I hope you can go to the problems 4.11 and 4. So these are very big problems. So if you feel like you try to understand the problem, if you feel that sir it has to be done, it's better if it's done on the class, I can always do that for you. Just try to see if you are able to understand that one from your end initially, then I will always be doing that problem. So this chapter is over actually, bending. So as you can understand, as in as in your mechanics, these chapters don't have any end actually. So I can give you any number of configurations and any number of problems can be formed. But the basic things and the basic concepts remains the same. So it's always, so I am having a beam like this. So এইখানে দেখো there is a load P. Here I am having a load P, right? So here I am having two supports actually. So there will be certain reactions. So let the reactions, let us call them as RA, and this reaction, let us call them as RB. So what will be the RA plus RB? So if I write the now statics equation, so RA plus B will be equal to 2P. Now you calculate the moments about the points A and B. So this is your A, B, C, D. So you do sigma MA is equal to 0. So you find out the moments of everything and all. So you'll be coming to RA is equal to P and RB is equal to P. So this one is equal to P and this one is equal to P. So now let's find out what is the moment at the in a portion AB. So let us take a cross section at a portion somewhere around AB, somewhere in between of AB. So right now, let us take a section at a distance small x from the end AB of the beam. So this is the end A of the beam. So at the end A, I am having an upward force of capital P, and this is the cross X. So let us calculate. So the point A. So if I write like M is equal to 0, so I should be having Mx is equal to, ठीक है, you just find out. So this one is x actually. So mx minus px is equal to 0, which makes mx is equal to x. So this linear variation along x. So at x is equal to 0 means ma. So at ma is equal to 0, and at a, what was that length? Let us take it as a. So at b point, so mb will be equal to pa. ठीक है sir?
Yes, sir.
Okay. So this is about. So this is we are done with the part. So this is about a section within AB. Now let us consider a section on the portion BC. So what I am doing is I am taking a portion. I am taking a section at a distance small x on BC. So now let us write the free body diagram for this one. So let's draw the free body diagram for that. So what I am having is now this one. So at A, I am having a force of P. At B, I am having a downward force of P. And then I am having the cross section XX. And then this is let MX. Let it be MX and let this distance be small a. Achha, I have taken the cross section at a distance of small x from the end A. So this is A, this is B. So now I am section BC. So if I write a moment balance equation, so sigma m will be equal to 0. So since sigma m is equal to 0, so I will be having mx. So what will be the moment of this force? So that will be clockwise. So minus px, and this for this force it will be again be anti-clockwise. So plus p into x minus a, that is equal to 0. So I should be having mx is equal to pa. So as you can see that for the portion BC actually, the moment is actually constant and equal to pa. ठीक है? And similarly the last part you complete it by yourselves, and you will be seeing that we are left with. So now if I draw the free body diagrams, so if I draw the bending moment diagram now, so let us take the points. So for the point B, this is B, this is the point C, and this is the point A. So this is I am having A, B, C, D. ठीक है? So at the point B, so what is the moment at the point A? It is 0. Then it varies linearly. So if you see the variation is linear. So mx varies as, I have deleted that one. So mx varies as px. So at the point A it is 0. At the point B it should be pa. So This is PA. This one up to this is constant, and again it will decrease to 0. So this is the final bending moment diagram for the portion ABCD. So you can see that for the portion AB, the bending moment is not constant, it changes from A to B. And for the portion CD, the bending moment is again not constant, it varies with X. But for the portion BC, the bending moment is constant. So we can say that this portion BC is in pure bending. And we haven't drawn the shear force diagram. It আমরা পরে discuss করব shear force diagrams and all. When we draw the shear force diagram also, you will see that the shear forces on the portion BC will be 0. So BC portion, that is under pure bending. Why? Because number one, it is having a constant bending moment equal to PA, which doesn't vary with X. And number two is the shear forces acting on the portion BC will be 0. So I haven't drawn the shear force diagram, not to make it too much complicated or to divert our attention from the bending moments and all. Okay? So this is how we draw a bending moment diagram, and from the bending moment diagram we can see that the bending moment is constant from the portion B to C. So for the point B it is PA, it is PA at C. So in between also at every point the bending moment is PA. But for these portions, bending moment M varies as X. For this portion also M varies as X. But for this portion M is equal to constant. So that is why this portion B